Dear students, this video contains a brief explanation of the experiment wavelength determination of laser using transmission grating. The aim of the experiment is to determine the wavelength of laser beam using a plane transmission grating. The experimental setup is shown in this figure. Apparatus used in this experiment include a semiconductor laser source, plane transmission grating, optic bench, vertical stand with a screen, and a white paper. Coming to the theory part, I will first explain the theory of laser action and then the theory of diffraction in detail. Laser is an optical device that amplifies light. It is a device that emits a strong, monochromatic, collimated, and highly intense beam of either visible or invisible electromagnetic radiation. Laser light is highly powerful. It is capable of propagating over long distances and is not easily absorbed by water. As we know, laser is the acronym for light amplification by stimulated emission of radiation. Laser has some unique characteristics which distinguishes it from ordinary light source. It includes temporal coherence or monochromaticity, which implies that laser is highly monochromatic. Then second property or characteristic is spatial coherence or directionality, which means that laser light is highly unidirectional. Then high intensity, since it travels along a particular direction only. Then unique polarization direction, and this laser beam is highly coherent. Now let us see the main components of a laser device. It includes an active material which represents the material having a metastable energy level and capable of producing laser output. Then we have a pumping mechanism to create a particular condition known as population inversion. Then we have an optical resonator to facilitate avalanche-like multiplication of photons. It consists of a fully reflecting mirror at one end and a partially reflecting mirror at the other end for trapping the photons emitted by stimulated emission of radiation, which in turn can result in laser beam of required amplitude and intensity. In order to understand the theory of lasing action, let me describe how matter interacts with radiation. A material medium is composed of identical atoms or molecules, each of which is characterized by a set of discrete allowed energy states. An atom can move from one state to another when it receives or releases an amount of energy equal to the energy difference between those of two states. It is known as a quantum transition. Consider two energy states E1 and E2 of an atom. E1 is the lower energy state while E2 is the excited state. As the constituent atoms of the medium are identical, the energy states E1 and E2 will be common to all atoms in the medium. Let N1 be the number of atoms in the lower energy state and N2 that in the excited state. Let a monochromatic beam of light is incident on the medium. The radiation may be viewed as a stream of photons, each photon carrying an energy h nu, where h is the Planck's constant and nu is the frequency of incident radiation. If h nu is equal to E2 minus E1, the interaction of radiation with matter leads to the three distinct processes in the medium, that is stimulated absorption, spontaneous emission, or stimulated emission. Now let me describe stimulated or induced absorption. If a system that may be atom, molecule, or electrons is initially in the lower state, energy state 1, it can rise to a higher state 2 by absorbing a quantum of radiation or photon of frequency nu, which is given by nu is equal to E2 minus E1 by h. This process is known as stimulated absorption or induced absorption. Now the second process is spontaneous emission. So if an atom or molecule lies in an energy state that is higher than the lowest or ground state level, it can spontaneously drop to the lower level without any outside stimulation. One possible result of dropping to a reduced energy state is the release of the excess energy as a photon of light. Excited atoms or molecules have a characteristic spontaneous emission time, which is the average time that they remain in the excited higher energy state before they drop to the lower energy level and emit a photon. Assume that an atom is initially in the higher energy state 2. Excited state with higher energy is inherently unstable. Hence, an atom in the excited state does not stay there for longer time and it jumps to the lower energy state 1, emitting a photon of frequency nu. This is known as spontaneous emission of radiation. If there is an assembly of atoms, the radiation emitted spontaneously by each atom has a random direction and phase and is incoherent from one atom to another. Now, stimulated or induced emission. While in the excited state, if the atom is illuminated with an incoming photon having exactly the same energy as the transition, the atom may be stimulated by the incoming photon to return to the lower state and simultaneously emit a photon at that same transition energy. A single photon interacting with an excited atom can therefore result in two photons being emitted. If the emitted photons are viewed as a wave, the stimulated emission will oscillate at the incoming light's frequency and be in phase or coherent, resulting in amplification of the original light wave's intensity. Thus, according to Einstein, an atom in an excited state may, under the influence of the electromagnetic field of photon of frequency nu incident upon it, jump to lower energy state emitting additional photon of same frequency nu. Thus, it is very clear that laser is produced by means of stimulated emission of radiation, as we require a highly coherent beam of radiation as output. In addition to stimulated emission, the other two important prerequisites for the generation of laser includes the existence of a metastable state and population inversion condition. Let us see each of them in detail. First one is population inversion. The primary problem in achieving stimulated laser emission is that under normal conditions of thermodynamic equilibrium, the population, which represents the number of atoms or molecules at each energy level, is not favorable for stimulated emission to occur. Because of the tendency of atoms and molecules to spontaneously drop to lower energy levels, the number of atoms at each energy level decreases as the energy increases. In other words, virtually all of the atoms or molecules are in the ground state for a visible wavelength energy transition. So this figure represents the distribution of atoms or molecules or ions of the active material under normal conditions of temperature and pressure. As we can infer from the figure, there exists a larger number of atoms in the ground state compared to that in the excited state. Moreover, the number of atoms in the excited state decreases exponentially under normal conditions. By means of suitable pumping mechanisms, it is possible to excite the ground state atoms or ions or molecules to the excited states. So this second figure shows the case when there exists a larger number of atoms in the excited state when compared to that in the ground state. So this represents the population inversion condition. The mechanism by which stimulated emission can be made to dominate is to have more atoms in the excited state than the lower energy state, so that the emitted photons are more likely to stimulate emission than to be absorbed. Because this condition is the inverse of the normal equilibrium condition, it is termed as population inversion. As long as there are more atoms in the upper energy level than the lower, stimulated emission can dominate and a cascade of photons results. The first emitted photon will stimulate the emission of more photons. These subsequently stimulate the emission of still more and so on. The resulting cascade of photons grows, resulting in the amplification of emitted light. If the population inversion terminates, spontaneous emission will again become the favored process. Now I will describe the metastable state. To achieve population inversion, we must have metastable states. Metastable states are excited states where the electrons stay for unusually long time. Normally, an electron in an excited state will make the transition to the lower state in a time of 10 raised to minus 8 seconds. In contrast, an electron may stay in a metastable state for 10 raised to minus 3 seconds. Hence, population inversion occurs only between the metastable state and the next lower state, which is the ground state here, and because of which laser emission occurs. As mentioned earlier, a laser requires three basic components for its operation: an active medium or active material, an energy source or pump source, which is also known as excitation mechanism, and a resonant cavity or an optical resonator. The active medium is a material in which the laser action is made to take place. It amplifies light. It may be a solid, liquid, or gas. The very important characteristic requirement of an active medium is that population inversion should be possible to achieve in it. The second important component is the pump source. It is an external source which supplies energy to obtain population inversion. The energy supplied by pump excites the atoms to higher energy levels through spontaneous emission or through non-radiative processes. The lifetime of the metastable state in which population inversion occurs must be very large as compared to the normal lifetime of the excited atoms in any other energy state. The process of raising the atoms or molecules of the active medium to high energy states is called pumping. The commonly used pumping methods are optical pumping, electrical pumping, inelastic atom-atom collision, chemical reaction, and direct conversion. In optical pumping, a high-intensity light source such as a flash lamp is used to excite the active medium. In electric discharge method, an extremely high electric field in an electric discharge accelerates the electrons emitted by the cathode towards the anode. Collisions between these high-energy electrons and the active medium produce molecules and ions of the medium in excited state, producing a state of population inversion. Inelastic atom-atom collision method is suitable when we have two types of atoms in the active medium, example helium-neon laser. Here, an electric discharge raises one type of atoms to their excited state. These excited atoms collide inelastically with the second type of atoms, exchange energy to these atoms, and then excite them to the excited states, thus achieving population inversion between the required levels. This ultimately results in laser action. In a chemical laser, the energy required to pump a laser comes from a chemical reaction. In direct conversion, electrical energy is converted into radiation, which occurs in LEDs and in semiconductor lasers. The third component of a laser is the optical resonator. It consists of two mirrors and it confines and stores light at certain resonant frequencies. It may be viewed as an optical transmission system incorporating feedback. Light circulates or is repeatedly reflected within the system without escaping. In a laser, to generate high intensity outputs, the light is directed back and forth through the medium. So for this, the active medium is placed between two mirrors. One is fully reflecting and the other one is partially reflecting. Such an arrangement is known as a resonator. It is also clear that a material with two possible levels of energy can never produce laser output. Here I will explain the reason in detail and show you why a 3 or a 4 level laser system is preferred for a laser device. In the 2-level system, where the atoms or molecules of the active medium can exist in only 2 possible energy levels, once the population inversion is achieved, the laser action would occur, but immediately it would end up with more atoms in the lower state. Such 2-level lasers involve a more complicated process. Achieving population inversion in a 2-level atom is not very practical. Such a task would require a strong pumping transition that would send any decaying atoms back to its excited state, since a ground state is involved in the laser action. It can be done but is very energy costly and inefficient. In a sense, the pumping transition would have to work against lasing transition. So this figure shows the distribution of atomic or molecular population obeying Boltzmann distribution law. The atoms originally in the ground state having energy E1 are excited to a higher energy state with energy E3 by an external source of energy such as xenon flash lamp. In this case, decaying back to the ground state also occur, but these atoms can be pumped back to the second state again. The first excited state is a long-lived or a metastable state which allows the atoms to wait photon while building up population of atoms in the state. The lasing transition in this laser is due to the decay of atoms from the first excited metastable state to the ground state. If the number of atoms in the ground state exceeds the number of atoms that are pumped into the excited state, then there is a high likelihood that the lasing photon will be absorbed and will not get sustained laser light. The fact that lower lasing transition state is the ground state makes it rather difficult to achieve efficient population inversion. As lasing starts, the population in the ground state increases, and as a result, it is possible that the photons emitted by stimulated emission are reabsorbed, thereby removing the photons that might contribute to the lasing action. Hence, it is not possible to continuously maintain the upper laser level more populated than the lower laser level. So, the output of a 3-level laser is not continuous but consists of pulses of laser light. A 4-level laser system is illustrated in this figure. On pumping, the atoms are lifted from the ground level to the highest of the 4 levels, E4, involved in this process. From this level, the atoms decay to the metastable state E3 and the population of this state grows rapidly. If the lifetime of the 4 to 3 transition, that means this transition, is short and that of 3 to 2 transition is long, population inversion can be achieved between the levels 3 and 2 and can be maintained with moderate pumping. Here, the lower laser level is not the ground state, but it is the first excited state. As a result, even a pump that may not be very efficient could produce a population inversion so long as the upper level of the laser transition is longer lived than the lower level. There are many different types of lasers depending on the type of active medium used. The laser medium can be a solid, gas, liquid or semiconductor. Lasers are commonly designated by the type of lasing material employed. Have a look at this table showing the different types of lasers and their peculiarities, like the active materials, pumping mechanisms used, and the type of resonator suitable for producing laser output. The laser used in this experiment is a semiconductor laser. Gallium arsenide, indium phosphide, gallium antimonide, and gallium nitride are all examples of compound semiconductor materials that can be used to create junction diodes that emit light. Aluminium gallium indium phosphide diode laser is used in our experiment to provide the red light of 650 nanometers wavelength and 3 milliwatt power output. Now let us study the working mechanism of a semiconductor laser in detail. Any semiconductor laser is nothing but an LED with heavily doped or degenerate P and N regions with forward biasing beyond a threshold value. When a PN junction having heavily doped P and N regions is forward biased by connecting the P terminal to the positive and N terminal to the negative of a direct current source, the electrons and holes combine across the depletion region to produce radiation. The photons thus produced may interact in three different ways. First one, an electron in the valence band can absorb the incident radiation and be excited to the conduction band, leading to the generation of electron-hole pairs. Second process is an electron can make spontaneous transition in which it combines with hole and in the process it emits radiation. Third one is the stimulated emission may occur in which the incident radiation stimulates an electron in the conduction band to make transition to the valence band and in the process it emits radiation. If the voltage across the P and N region, that means the PN junction, is very large, the injected carrier concentration would be large. In such a case, the stimulated emission can exceed the absorption, producing amplification in the active region, which results in a good light output. To convert the amplifying medium into a laser, optical feedback should be provided, and it is done by cleaving and polishing the ends of PN junction diode at right angles to the junction. In this figure, the white region represents the depletion region. A resonant cavity is formed by just cleaving the junction ends. The light that is trapped is reflected back and forth between the two phases. The other two sides are rough and therefore suppress oscillations in unwanted directions. The active region is a little wider than the depletion region. The output is also not as monochromatic as a gas laser. A commonly used semiconductor laser is gallium arsenide. In semiconductor laser diodes, population inversion occurs in conduction band. When laser diode is forward biased, electrons from N side and holes from the P side diffuse into the depletion region where both carriers recombine. The result of recombination in direct band semiconductors is the production of light photons. Under forward bias condition, when drive current through electrical connections reaches threshold level, population inversion results and a coherent radiation emerges out. This figure shows the energy level diagram of a gallium arsenide semiconductor laser. In semiconductor materials, electrons may have an energy within certain bands. This lower energy level is known as the valence band, and the upper region is called the conduction band and represents this energy states of free or conduction electrons. Electrons may have energies in either of these bands but not in the gap between the bands. So this figure, the first figure, shows the relative population of energy bands on both sides of P and PN junction with no voltage applied to the diode. The N-type material contains electrons which behave as the current carriers in its conduction band, whereas the P-type material has holes for carriers in its valence band. When a forward bias is applied to the diode, the energy levels are caused to shift as seen from this second figure. Under these conditions, there is a significant increase in the concentration of electrons in the conduction band near the junction on the N side and the concentration of holes in the valence band near the junction on the P side. The electrons and holes recombine and energy is given off in the form of photons. The energy of photon resulting from this recombination is equal to the energy associated with the energy gap. This energy is often in the form of electromagnetic radiation. In light emitting diodes, that means LEDs, this light energy is transmitted out through the sides of the junction region. However, in semiconductor lasers, the junction forms the active medium and the reflective ends of the laser material provides feedback. Now this figure illustrates the transition from spontaneous emission to stimulated emission by plotting the relative optical output power and input drive current of the semiconductor laser diode. The lowest current at which stimulated emission exceeds spontaneous emission is known as the threshold current, that is this value. Thus, below the threshold current, the system acts as an LED only, and if the input current is above threshold value, stimulated emission occurs, resulting in laser output. So this represents the figure of an LED. LED is merely a forward bias PN junction device which generates light by the recombination of electrons and holes at the depletion region. When biased by means of injection pumping, electrons and holes are injected into the depletion region. Inside the depletion region, electron-hole recombination takes place, producing light corresponding to the respective band gap. It is spontaneous emission. Now let us see the difference between LED and a semiconductor laser diode laser. So in the case of LED, light is emitted due to spontaneous emission, whereas in the case of a laser, light is due to stimulated emission. The output of an LED is polychromatic, whereas the output of a laser, semiconductor laser, is monochromatic. LED lacks directionality. Light emitted by an LED lacks directionality, whereas the laser light is highly directional. Intensity is very less in the case of an LED, whereas the output of a laser is highly intense. Thus, it is clear that forward biasing the PN junction diode with a current I greater than I threshold results in the generation of laser mode. Once laser is produced, you can measure its wavelength. Since wavelength of light is of the order of certain nanometers, it is clearly not something that can be measured as easily or as simply as units of weight or distance. Hence, here we use an indirect method of calculating the wavelength of light simply by allowing the light to diffract and thereby measuring the angle of diffraction of the light. In order to diffract light, generally light coming out of that source is allowed to pass through an optical element called a plane transmission diffraction grating, shown here. A transmission grating consists of a system of equally spaced slits. It is made by rolling a series of closely spaced parallel lines with a diamond pointer on an optically transparent sheet of material. The distance between the corresponding points of the adjacent slits is called the grating element, which is represented by D. And if the width of the transparent portion is A and that of opaque portion is B, then the grating element is given by D is equal to A plus B. Then the wavelength corresponding to each diffraction angle can be calculated by using the grating equation sin theta is equal to nn lambda. Hence the wavelength of each prominent line is given by lambda is equal to sin theta by nn. Now let me describe the procedure in detail. Mount the semiconductor laser horizontally so that it produces a horizontal laser beam. This is the laser source and it is a diode laser which emits red light. The wavelength of light emitted is 650 nanometers and its power is 3 milliwatt. You can adjust the intensity of laser beam emitted with the help of these screws. Now the given plane transmission grating is held vertically using an upright at a distance of about 30 centimeters from the laser source. This distance between the laser source and the grating is kept as 30 centimeters. A screen is placed at a distance L from the grating, which is usually taken as 400 centimeters. Now the grating is mounted here and you can see a white screen just behind this grating, and the distance between this grating and the screen is taken as 400 centimeters or 4 meters. Fix a sheet of white paper on the screen. When the current is switched on, a beam of laser light is incident normally on the transmission grating, and the laser beam is diffracted into different angles, and hence we get clear, well-defined and bright images or spots on the white paper. Now the screen is moved to a fixed distance L, and a collection of spots is obtained on the screen. At the middle, the central maximum is obtained, while on either side of this central maxima are higher order maxima. First order, second order, third order maxima on both sides of this central maxima. Trace the position of the spots on the white paper. This shows the distance between the first order maxima on both sides of the central maximum, and this distance is taken as 2x. Now measure the distance between the grating and the screen with a thread and take it as L, which in this case is 400 centimeters. This figure shows the distance between the two second order maxima on both sides of the central maximum, and the distance is taken as 2x itself. Similarly, this figure shows the distance between two third order maxima on both sides of the central maximum, and again the distance is taken as 2x. Now the experiment is repeated for different values of L, say 425 centimeters, 450 centimeters, etc. Now take out the paper from the screen and measure the distance between spots. You will get a pattern like this, and the pattern consists of the central maximum followed by first order maxima on both sides of it, then second order maxima on both sides of it, and the distance between the grating and the screen is taken as L. This is the observation column. The distance between the first order spots on both sides of the central maximum is measured as 2x centimeters. From this, calculate the value of x. That means 2x divided by 2 is x. The distance between the grating and the center of the screen is measured as L centimeters, which in this case is 400 centimeters. So you can easily calculate tan theta, which is x by L. From that, find out the value of theta. Theta is nothing but tan inverse x by L. So once theta is calculated, the angle of diffraction is known. You can easily calculate lambda, since we are dealing with first order, and capital N is 150 lines per centimeter. It represents the number of lines per unit length of that grating, and which in this case is taken as 150 lines per centimeter. So for the first order, lambda can be easily calculated using sine theta by nn, where small n is equal to 1 and capital N is 150 lines per centimeter. Similarly, calculate the value of lambda corresponding to small n is equal to 2. So again, the distance between the two second order maxima is taken as 2x itself. From that, find out the value of x, then tan theta, then theta, and substitute the value of that theta in this expression. But here the order is 2. So put small n as 2 for this calculation. For this one, third order, again the same process is repeated, but put small n is equal to 3 in this equation. Calculate the value of lambda corresponding to that particular distance, say 400 centimeters. Repeat the experiment for different values of L, say 425 centimeter, 450 centimeters, etc. You will get a set of 9 values here. Take the average of these 9 values. That will actually give you the wavelength of that laser beam. Thank you.